This video tutorial is about oxidative phosphorylation and chemiosmotic theory. The final stage of aerobic respiration is oxidative phosphorylation, the production of ATP in the presence of oxygen. Oxidative phosphorylation takes place in the mitochondria. It involves electron carrier proteins arranged in chains called the electron transport chains, which are embedded in the inner mitochondrial membranes, as well as a process called chemiosmosis. The folded cristae give a large surface area for the electron carrier proteins and ATP synthase enzymes. Reduced NAD and reduced FAD are reoxidized when they deliver their hydrogen atoms to the electron transport chain. The hydrogen ions released from the coenzymes split into the protons and electrons. The protons go into solution in the mitochondrial matrix. The electrons from the hydrogen atoms pass along the chain of electron carriers. Each electron carrier protein has an iron at its core. The iron can gain an electron, becoming reduced, so it becomes Fe2+. The reduced iron can then donate the electron to the iron in the next electron carrier in the chain, becoming reoxidized to Fe3+. As electrons pass along the chain, some of their energy is used to pump protons across their inner mitochondrial membrane into the intermembrane space. As protons accumulate in the intermembrane space, a proton gradient forms across the membrane. Proton gradients generate a chemiosmotic potential that is also known as a proton motive force, or PMF. They are a source of potential energy. ATP is made using the energy of the proton motive force. Protons cannot easily diffuse through the lipid bilayer of the mitochondrial membranes, as the outer membrane has a low degree of permeability to protons, and the inner membrane is impermeable to protons. Protons can, however, diffuse through the proton or protein channels associated with ATP synthase enzymes that are in the inner membrane. As protons diffuse down their concentration gradient through these channels, the flow of protons causes a conformational or shape change in the ATP synthase enzymes that allows ADP and PI to combine, forming ATP. The flow of protons is known as chemiosmosis. It is coupled to the formation of ATP. The formation of ATP in this way, in the presence of oxygen, is oxidative phosphorylation. Oxygen is the final electron acceptor. It combines with electrons coming off the electron transport chain and with protons, diffusing down the ATP synthase channels, forming water. So the equation is 4H plus 4E minus electrons and protons combining with oxygen to form 2 water molecules. The diagram on the slide in front of you just shows this same process again. I'm going to give you a moment to read the information on this slide. Here we see the same series of reactions again. This is the electron transport chain. So how much ATP is made during oxidative phosphorylation? The table 1 at the top of the slide in front of you shows the number of reduced coenzymes formed during respiration. The reduced coenzymes provide both protons and electrons to the electron transport chain. The protons and electrons from the 10 molecules of reduced NAD can theoretically produce 25 molecules of ATP. The protons and electrons from the 2 molecules of reduced FAD can theoretically produce 3 molecules of ATP. Oxidative phosphorylation may therefore produce 28 molecules of ATP per molecule of glucose. Table 2 shows the ATP yield per molecule of glucose at each stage of respiration. This theoretical yield is rarely achieved, and the actual yield may be closer to 30 molecules of ATP per molecule of glucose, or even less, because some ATP is used to actively transport pyruvate into the mitochondria. Some ATP is used in a shuttle system that transports reduced NAD made during glycolysis into the mitochondria, and some protons may leak out through the outer mitochondrial membrane.